Hello students, welcome to the class of digital signal processing. We were studying properties of DFT and we have already done almost all the property, only two were left, correlation and circular correlation in Parseval's theorem. So let's complete it, and with that we will be completing the properties of DFT. Okay. So circular correlation. Again the word circular because of capital N, that is you are going to shift it with the boundary of capital N, finite number of signals, and correlation, as you know, you are doing the convolution between xn and y star n. The two signals are xn and yn. So the same thing as convolution, but here you are going to take xn and y star n. That is the only difference that we have. So let us start with this part. So what does it the expression is in this way, that is Rxy. Correlation between x and y is denoted by Rxy. And when you are doing the shifting with respect to m, with the m, then the variable is n. And then n is small n is equals to 0 to capital N minus 1. Now here it is going to be xn y star n minus n modulo of n. So this is the circular correlation. Because of this n, it is coming at here as n minus n. Now, for the DFT case, what we have to show that DFT of this part, that is the circular correlation of xy, the DFT of the circular correlation of xy is given as xk into y star k. That is it. Let's go ahead and do the proving for this part. So for the proof, what we are going to do is we'll start from the right hand side where we have xk and y star k, and we will take the inverse DFT of this. If you take the inverse DFT of this, what is the formula going to be? Okay. So here you will have to write 1 by n, k equals to 0 to n minus 1. And this whole thing you are taking as a single unit. So xk, y star of k e to the power j 2 pi k n by capital N. Now next thing, we have to write the value for this part and this part in terms of DFT. Okay, so how we will be doing that? K equals to 0 to capital N minus 1. Now again we will write the summation n equals to 0 to n minus 1 xn e to the power minus j 2 pi k n by n. And also for this y star k, n equals to 0 to n minus 1 yn e to the power minus j 2 pi k n by n. Just put a conjugation here. And then finally, you have e to the power j 2 pi k n by capital N. Now, just what we are going to do is we will change these values. Which values are we going to change? The values of n. See, both the places we have written n. Both the places we have basically n. Small n and small n here. So this both we will change it. So 1 by n, k equals to 0 to n minus capital N minus 1. In this n, I will make it n equals to 0 to n minus 1 into xm. The next one will be, let us take it, this one, let us take it p. So p equals to 0 to n minus 1, y star p. Now I will, in the same time, I am going to write all the e to the power together. So it is e to the power minus j 2 pi by capital N. Also k is common. See, k is here. In this also you have k, in this also you have k. So I wrote it as, if I take plus over here, then it is e to the power j 2 pi k by capital N. What are we left within is C. Okay, it will be better if I do this part a bit later. So what I'll do is, first I will write it as it is so that we see the variables here, e to the power minus j 2 pi k m by n. Now I will take here p equals to 0 to capital N minus 1 by p e to the power minus j 2 pi k into p by n, and this is inside the conjugation, and the whole thing is e to the power j 2 pi k n by n. Now I will take xm yp outside, 1 by n, m equals to 0 to n minus 1, xm, p equals to 0 to n minus 1. Now here this yp I will change to y star p. Okay. Now this k equals to 0 to n minus 1, I'll put here k equals to 0 to n minus 1. And all the e to the power j 2 pi k n. E to the power j 2 pi k by capital N. And see over here you have minus m. Here you have minus p. And here you have plus n. Okay. Now if you see this part, let n minus m minus p is equal to integral multiple of qn. The integral multiple of n, so I'm writing it as qn. So what will happen here? 1 by n. This is going to remain as it is. N is equals to 0 to n minus 1 xm. This is going to remain as it is. P is equals to 0 to n minus 1 y star p. And this side is becoming k equals to 0 to capital N minus 1 e to the power j 2 pi k by n into qn. Now this n and this n get cancelled. Now again, I'm not copying the things. I'm writing only for this side. The rest of the things here, it is going to be the same. This thing is going to be copied here. So e to the power j 2 pi q whole raised to the power of k. Because k is changing and this whole thing is going to remain equal to 1. So e to the power j 2 pi q for any integral value of q. We know that q is an integer. So integral value of q e to the power j 2 pi q is equal to 1. Good. Now what we are going to do is k equals to 0, capital N minus 1, 1 to the power of k. Now 1 is getting added n minus k, from k is equals to 0 to n minus 1. That means it is getting added n times. So the answer is going to be n. Now if you see this whole portion here, this part is equal to, this part is equal to n. So now when I copy this full thing at the end, it's going to be 1 by n, m equals to 0 to capital N minus 1, xn, p equals to 0 to capital N minus 1, y star p into n. Now, this p over here, since we will try to convert it into one summation itself, so m equals to 0 to capital N minus 1, xm is okay. Now this p I will convert in terms of n, m and n. So here we had n minus m minus p is equal to qn. you had this relation n minus p is equal to q into n. So I can write it as n minus m minus qn is equal to p. So what I'll write here is y star n minus m minus qn. So this becomes equivalent to saying modulo n for this part. N minus m modulo n, capital N. N minus 1 xn y star, because it is a circular convolution. Now this is what? This is convolution. So since this is convolution, we started from xk into y star k, and where we landed is at this point, which is circular correlation. And hence it is proved that if you are circularly correlating the signal in the time domain, it is equal to the multiplication of the signal, individual Fourier transform of the signal, and with a conjugate of the one signal. So now last thing that we have to do is the Parseval's theorem. I just rewrite this thing. So what does it mean to say that circular correlation, which is denoted by this part, if you take the DFT of this, we are going to get xk into y star k. So this is called circular correlation, and this is multiplication, but not the simple one. You have to notice star, multiplication with conjugate. Multiplication of DFTs of each with one of them as conjugate. This is the circular correlation property. Now the last property that we have to do is the Parseval's theorem for DFT. That is very short. Let's do that. So Parseval's theorem, or you can say Parseval's relation, so Parseval's relations, first of all, let us write down the statement of this. That same way, if DFT of x1n is x1k and DFT of x2n is x2k, then by Parseval's relation, summation n equals to 0 to capital N minus 1 x1n into x2 star n is equal to 1 by n k equals to 0 to capital N minus 1 x1k into x2 conjugate k. So now what we are going to do is we will start from the right hand side. So on the right hand side, what we had was, so we are starting the proof. To start from the RHS side. On the RHS side, first write down what we had, 1 by n, fine, summation k equals to 0 to n minus 1, xk into y star k. Fine. Now write the DFT of one of this. So to actually not y, it's x2. Previously, I've taken x2, so let us write it x2 here. This is x1k and this is x2 star k. So write the DFT for one of them. So write it for this one. Let us say we will write it for k equals to 0 to n minus 1. If you write it for this one, it is going to be n equals to 0 to n minus 1 x1n e to the power minus j 2 pi k n by n. And the outside of this, you have x2 star k. x2 star k. Now, if you change the order of summation, take this outside, n equals to 0 to n minus 1 x1n, and write this full thing inside, that is 1 by n k equals to 0 to n minus 1 x2 star k e to the power minus j 2 pi k n by capital N. So, if you want to remove this x2 star k, means if you want to remove this star from here, that time you have to take it out. In that case, you will have to make this plus. So it is going to become n equals to 0 to n minus 1 x1n 1 by n. If I want to write x2 star k as only x2k, then there we have to make a change somewhere else, which is here e to the power j 2 pi k n by n. And then we are taking this conjugate outside here. Fine. Now this part is what? This is the IDFT of x2n. x2n star. This is from this one. If you see, it is from, this is x1n going from n equals to 0 to capital N minus 1. So it's going from n equals to 0 to capital N minus 1 x1n into x2 star. This is what you have to prove for the Parseval's relation. So let us see once more the Parseval's relation. The Parseval's relation says that x1n into to star n. If you take the whole summation of this part, means the energy content in the time domain is same as the energy content in the frequency domain. That is a major description of the Parseval's relation. Now here you are having what the 1 by n k equals to 0 to n minus 1. You started from that point. You started from here, the RHS of this. This was your RHS. So from here you started. Now you wrote the DFT for this one and left it as it is. Once you wrote the DFT and then you are changing the order of summation. This x1n, you put it outside, and this k equals to 0 to n minus 1. This one thing you have put it inside with clubbing with x2 star k and this one. Now the star, if you put outside, that time sign will change here also. So x2 k e to the power j 2 pi k n by n. And now finally we had x2 n star, x2 star n. This way we have proved the Parseval's theorem. So this is all about the properties of DFT. Everything is covered here. Now the next thing that we have to do will be regarding the FFT. And there are some questions which we can do of linear convolution and circular convolution. We will be doing all those again in the next class. Thank you.